So we have an optimization problem here. Find the shape of the right circular cylinder. So they mean find the R and the H, the radius and the height of the maximal surface area. So maximal surface area, including the top and the bottom. That's important. That can be inscribed in a sphere of radius R. So here's the picture of what's happening. This is a circular cylinder, right cylinder, inscribed in a sphere to fit inside there, and its top edge intersects with the edge of the sphere, and so does the bottom edge. And you have a radius of the cylinder and a height, and that's what we want. And then here's another picture over here on the left that shows more straight on view. So what are we trying to optimize? The surface area. So what is the surface area? It's the top and the bottom plus all around the sides. So when you cut a cylinder side and stretch it out, then as you can see, when it joins back to the front, it's gone one time around. So it's 2 pi r length around the top edge times the height. So when you take the can and cut it and then stretch it out, you get a rectangle, and it's 2 pi r long because that's across the top, and it's h high. So that's how you get this. So that's your surface area. Then you simplify it down and you get this. So that's your optimizing equation. Now you need a constraint. We're doing one variable calculus, so we need one variable, not two. So we have to constrain R to H. Well, we do have here, over here, we got this nice right triangle with the radius going from the center all the way to the edge of the sphere. We got H over 2 being half the height of the cylinder, and we have a radius of the cylinder, and so you see a right triangle relationship, which is going to come up in a lot of these geometric type. So H over 2 squared plus R squared over 2 equals R squared, and then you go from there and you solve for H. Then you substitute in the H in, and you get this, and you clean that up and you get that expression for the surface area depending on just the radius. And then we go on to the next page. Now we've got to take the derivative to find our local max, because we're looking for the maximum, the radius that maximizes the surface area. So it's a little bit difficult, but it does come out. We set it equal to 0 to determine the level points, go through all the algebra, clean it up down to here. Now this can be solved by the quadratic formula, because if you rewrite it like this, you see it's, if you view r squared as its own variable, such as like a z, you see if it's like 5z squared minus 5r squared z plus r to the 4th. So it is in a quadratic form where the exponents decrease: squared, first power, 0 power. So using the quadratic formula, but in terms of r squared, which is the variable, you go through the quadratic formula, you get the answers. Then we take the plus and minus square root, but we're not going to have a negative radius. So the candidates for the r or this one, or this one. Now, it's a little too cruel to plug those into S, although it would work, to see which one's larger. It's also a little bit too cruel to find the double prime of S, although it could be done, to check the concavity, to make sure it's concave down, so you have a maximum. So we go on to a different method. We use a trick of the calculus trade. Just let R equal 1. Because these dimensions are supposed to solve for any sphere, so just let R equal 1 and just see what happens there. See which R gives the larger S value. Okay, so here's your formula. Plug in 0.85 is one of the R's and 0.53 is the other. 0.85 evaluates in 10.17 and S of 0.53 evaluates out to about 7.41. So the winner is the 10.17. And since we have this technology available to us, we check it, we graph it. This is for R equal 1. We graph the S of R function versus R, and you do see that this is 1. So at right around 0.85 right here, you do get your local max, which in this case is a global max, and that's your tells you that this R, which is in exact form is this one, is the actual local max. So this is your answer, and then you have to go and find the H. So the H is originally this quantity. Plug in the R, square it out, simplify some things, and get down to here. And so your cylinder shape will have radius, this radius, and this height.